Geometry has to do with space and distances, shapes, size, and relative positions of figures. It has many applications, for example, in natural science and in navigation and architecture, for example. In geometry study, some concepts, fundamental concepts like a point. A point in geometry is just something that doesn't have any size. It's just a point in space. And lines, by which often mean a straight line. To be precise, one should distinguish between a line. It actually it's infinitely long. Otherwise, you talk about the line segment. And the line segment, you have 2 points, and then endpoints, and then you have the line, finite line in between them. And you can also talk about rays. And the ray has one starting point or end point, and it's infinite, goes infinite from there. Then one also has the concept of a plane. And the plane, a two-dimensional plane, then we could study curves and lines in this plane, or points in this plane, for example. So these are some fundamental concepts when it comes to geometry, to study these. And then we will also come to three-dimensional space later on. But we will start with plane geometry. That is, we only study things like plane, lines, and points. And later on we will study three-dimensional bodies instead. So plane geometry, or Euclidean geometry, it's based on some axioms in its foundations. So that these are some things you take for granted that are true. And from these, the rest of the geometry follows with logical deductions. So by using axioms, concepts, and definitions, other theorems will follow. But for example, some axioms in plane geometry is that, for example, if you have 2 points, then there is exactly one line that will go through these 2 points. Okay, it's a little bit hard to draw here, but so if I draw like this, but what we actually mean now is an infinite line. So if you have 2 points, this axiom says that we have exactly one line going through these 2 points. And if we have a line, another axiom says that if we have a line and we have a point outside this line, there is exactly one line going through that point that will never cross the first line. So these are parallel. So if you have 2 lines, L and L prime, you denote that they are parallel. You write like with 2 parallel lines like this. So that means that no matter how far you go along the lines, they will never intersect. So from axioms like this, you can build up the whole geometry, Euclidean geometry or plane geometry. If you have 2 lines intersecting, then you will have an angle between here. So you have an angle. And how large is this angle? Well, if you draw a circle with its center in this point here, where they intersect, then you see how large part of the circle is this. Okay, one complete circle is 360 degrees, or 2 pi radians. And then to find out how large part is this, then for example, if this is 10% of the circle, then it's 36 degrees. 2 pi divided by 10 if in radians. So this way you measure angles between two arms. These are called arms. And you can have, for example, you have a triangle. You have angles between the sides of the edges of the triangle. So for example, if you have a fourth of an angle, of a complete circle, that is, like this. So if you have a complete turn here, then it's 360 degrees. So if you divide it in 4 equal parts, this will become 360 degrees divided by 4, so 90 degrees. And this angle here, then you often denote it by like this, because it's 90 degrees. Or if you have it in radians, you have 2 pi divided by 4, so pi half. That's the same as 90 degrees. The choice of 360 for one turn, there's historical reasons for that. But it's good actually to have for 360 degrees because it's divisible by many numbers. You often end up with an integer angle. And having 2 pi as radians, that has to do with the circumference of a circle is 2 pi r. So that comes from the definition of radians. So the reason you have 2 pi for a turn in radians is that if you define angle in terms of radians, like if you have this arc length of this one, so in this case the arc length of that one is 2 pi r, but the fourth, so this is the circumference of a circle, divide that by 4, you get the arc length here. And if you divide that by the radius of the circle, that's the per definition how many radians there are, and this becomes pi half. So if you instead have one complete circumference and divide by r, you get 2 pi. So that's one turn is 2 pi. So if you have an angle smaller than 90 degrees, that is a fourth of a turn, so smaller than 90 degrees, you call it acute angle. Not acute angle, but acute angle. So if it's smaller than 90 degrees. And then, of course, if you have 90 degrees, you call it a right angle. And then you draw it like this just to indicate that it's 90 degrees. So then it's called a right angle if it's 90 degrees. And if the angle is larger than 90, so if V is larger than 90, you call it obtuse angle. And these two sides here of the angle, they're called arms, the arms of the angle. And then if you have, for example, a triangle, then you have an angle here. So you have an angle here. These sides here in the triangle are called adjacent sides to the angle. And this is called the opposite side to the angle. And this is also an adjacent side. And if you take this side, then this angle is an opposite angle of this side here. So if you call it AB, so it's opposite side of the side AB. Like we see here that much of geometry has also to do with the definitions. You have to define a lot of concepts before you can have a language talk about shapes and sizes. For example, if you have two lines crossing or intersecting, then you have angles here, here. These two, that by the way are equal. So if you have two lines intersecting, straight lines intersecting, these will always be equal. And they are called vertical angles. and these two, A and C. A and C are called supplementary angles. So A and B, they're called vertical angles in respect to each other. And A and C are called supplementary angles in respect of each other. So the sum of these two supplementary angles are 180 degrees, since that's half a turn. And like I said, these two are equal. And that follows from the fact that that angle plus that is 180, and that plus that also 180, and that then it follows that these are equal. So you have that A plus C is 180 degrees because they're supplementary, and B plus C is also 180 degrees because they're also supplementary. And then if we subtract the first one, we can, for example, we can subtract A plus C and subtract the other one, B plus C. And then we also subtract these sides, since that one is 180, that was 180. So this side becomes 0 degrees, so this minus this. Then we see here that the C's will cancel. And then it follows that A minus B is equal to 0 degrees. That is, A is equal to B. If you have two lines intersecting and the angle between the lines, this one, is 90 degrees, then you say that these two lines are perpendicular. So these are perpendicular lines. You also say that this line here is a normal to this one. It's a normal to that one. And oppositely, this one is a normal to that one. And that's because they are perpendicular. So they are normal to each other. That is normal. So let's say we have 2 points. We have a line segment connecting 2 points. And let's say this is the middle point, so they're equidistant here. And we draw a normal here, a line perpendicular through this middle point. So we have 90 degrees here. Then this one is called a perpendicular bisector to this one. So if this is a middle point here, middle point to this line segment, this is a perpendicular bisector to this one. We can also talk about a bisector for an angle. So if you have an angle here, and if you have a ray here dividing this angle into two equal parts, so this angle is equal to that one, then this is called an angle bisector. This ray here is an angle bisector to this angle. If we have a plane figure made up of straight lines, for example like this, then that is called a polygon. So there's a figure made up of straight lines. It's a polygon. And here we have edges and vertices. So these are edges, these are the vertices. If we have a polygon with 3 sides, then it's of course is called a triangle. So a polygon with 3 sides is called a triangle. And if it has 4 sides, then it's called a quadrilateral. And if it has 5 sides or edges, then it's called a pentagon. So these are sides, or are called edges, and these where they cross are called vertices. If we draw a straight line between two vertices like this, or like that for example, these are called diagonals of the polygons. If you have a polygon where all the sides, all the edges are equally long, are the same size, and all the angles are also the same size. So if we write like this, let's call it A. Or for example, if you have a quadrilateral and all the sides, all the edges are equally long, same size, and then all the angles here are 90 degrees, they're all the same, then it follows that are 90 degrees. These are examples of regular polygons. So if they have the same edge length and same angles, they're called regular polygon. So if they do not have the same angles and size of the edges, they are just called a polygon. Let us look a little bit closer at triangles. So let us limit ourselves to polygons that are triangles. So three edges and three vertices. Okay, in a triangle, the sum of the angles, let's call it A, B, and C. The sum of the three angles in the triangle equals 180 degrees. So half a turn. So how can you show that? Yeah, there are different ways of showing it, but let's extend this line here. Or maybe do it more carefully like this. So I extend the edges like this. And then imagine that I start at this point here. So I start at one of the vertices. Then I walk along the line here. Then I come here, I turn. I walk in this direction. Then I have to turn an angle here. Let's call it U. Then I continue here, and then I have to turn again. Let's call it V. And then finally I have to turn this. And that's W. So when I've gone one turn around, then I've changed direction. The total change in direction, the sum of these three, must be 360 degrees. Okay, so after one turn, I have turned 360 degrees. Then, let me exchange now what is U? We said U plus C, the supplementary angles. These two add to 180. So that means that U is 180 degrees minus C. So U can be written like this. So C is 180 minus C. V, in the same way, V is equal to 180 minus B. And W is also 180 degrees minus A. Three times 180, that's 540 degrees. And then we have minus A, B, and C. Let me now move this to the other side of the equation. And add, so I have this on the other side of the equation. Then this is 180 degrees. And here says A plus B plus C. So we have arrived at the sum of the three angles inside the triangle equal to 180 degrees. Let's say we have a triangle looking like something like this. Then we see that all three angles here are less than 90 degrees. So we have, for all angles, we have this. Then we say that this is an acute triangle. So if all three angles are less than 90 degrees, we say that it's an acute triangle. If we instead had one of the angles larger than 90 degrees, so let's say that this one, A, for example, it doesn't matter if it's B or C, but let's say A is larger than 90 degrees, then we call obtuse triangle. And if one of the angles is 90 degrees, then we have a right triangle. So if one of the 90 degrees, then we have a right triangle. Let's say we have a triangle where two of the edges have the same length. So this is supposed to be a triangle where two of the edges have the same length. Let's call it A. This triangle would have two edges same length. They're called isosceles triangles. So two edges are the same. If all three sides are the same, then it's a little bit difficult to draw here, but let's say that, imagine now that all three sides are edges are the same length. Then that's called equilateral triangle. An important special case of triangle is a right triangle. So it means that we have 90 degrees of one of the angles. And then let's call this A, B, and C. Okay, so this side here that is opposite to the 90 degrees, this is called a hypotenuse. So for a right triangle, we call this a hypotenuse. Och the other two are called cathetus. So these two are called that. And then we have the Pythagorean Theorem for a right triangle. And as you probably know, this says that if you take the squares of the cathetus, or catheti in plural, then the sum of those squares is equal to the square of the hypotenuse. So that's the famous Pythagorean theorem. And that is well used in many areas in mathematics. So let's say, for example, let's see use of Pythagorean theorem. Then we have, if you have a triangle, a right triangle, so let's say that this is 3, this is 4. What is this then? Well, let's call it C. Then we have, according to Pythagorean theorem, that C squared is equal to 3 squared plus 4 squared. So C squared is equal to 9 plus 16, 25. And that means that C is equal to square root of 25, 5. So we can, if we know two of the edges of the right triangle, we can find out the third. Or for example, if we instead would have known one cathesius and one the hypotenuse, we could have found out the third one. So let's say that this is 3 and this is 6 and this is we don't know whether this is, let's call it x, or let's call it according to the old other figure, let's call it b. Then we could solve it using Pythagorean Theorem, because we have 6 squared equal to sum of squares of these two. So 3 squared plus b squared. Okay, so this almost looks like a b, but so this is 36, 9 plus b squared. And then we have b squared equal to 36 minus 9, 27. And then b is equal to square root 27, approximately 5.2. So this is how you can use Pythagorean theorem to, for example, in this case, determine one of the lengths of the edges given two others. What is the area of a triangle? Okay, so if you have a triangle, looking like this, then we have the height of the triangle is this one. So the height, if we draw a straight line 90 degrees from this edge up to the vertices here, then this is the height. And this here we call the base of the triangle. Then we have that the area of the triangle is equal to b times h, the base times the height, divided by 2. And that can be easily proven by extending this to a rectangle and seeing that this area is half of that rectangle. We should also be careful to say what we mean by height if the triangle, for example, looks like this instead. In this case, we have the height here. So we have to extend this side here, then this one, and this, the height is here, and the base is this one. And then again it's given by this formula. So you just have to be careful what we mean by height. Let's take two edges here, or two parallel line segments. So these are two parallel line segments, and let's connect them here. So we get a quadrilateral. Since these two edges are parallel, this is called a trapezoid. This is called a trapezoid. So let's call that A, length here, and that B. Then we have the height of the trapezoid. If we draw a perpendicular line to the base, then this is the height of the trapezoid. Then you can calculate the area of the trapezoid using this formula. You take A plus B, dividing by 2, and then multiplying by the height. There is some important special case of a trapezoid. For example, if A and B equal, so if you have A equal to B, then it could be either a rectangle or it could also be a parallelogram. So if they are offset to each other. So these are special cases of a trapezoid. So let's say that this is equal to this. and also here. So this is a rectangle. This is a parallelogram. So in this case we have the height here. In this case we have the height here. In this case we have a special case of this formula. So for these two cases we have that A is equal to B. So this will become A times H. So this is just a normal way of calculating the area of a rectangle. One length here, the length of one edge multiplied by the other. So A times H. And also the same here for the height in the parallelogram. And of course a special case of a rectangle is a square. So if H and A are equal. So a trapezoid has these as special examples, particular cases. So these are just particular cases of trapezoid. So these are called also trapezoid. And also a square is a trapezoid, special case of a trapezoid. Let's just take a short example. So let's say we want to find out what is the area of this one if A is equal to 2 and 5 and B is equal to 4. Yeah, then we have the area is 5 plus 4 divided by 2. And what is then the height? Of course it could be anything, but let's say that the height is equal to 3. Because we could place this at any distance from each other we like. So then in that case this will be 9 divided by 2, 4.5 times 3. So 4.5 times 3, that's 13.5. Then we have another important case, special case of a figure in the plane. That's a circle. So if you take a point and then you draw all points equidistant from this point. So if you find all points are equidistant to that one, then you will find a circle. Okay, so let's just start with the circle instead here. So all points here on the circle have the same distance from this center point. The distance here is the same no matter where on the circle we are. So this is the center. This is called a radius. And here we of course have the circle. So if you have, let's enlarge the circle. So let's us draw a secant. And what is a secant? A secant is a straight line that intersects the circle at 2 points. So this straight line intersects here and here at 2 points. And it's called a secant. And if the secant goes through the center of the circle, like that, intersects there and there, then the line segment from A to B is called a diameter. And of course here's the center. So this half of the diameter here is the radius. The diameter is also a special case of a chord. So if you take 2 points on the circle and you connect them with a line segment like this, then this is called a chord. So a diameter is a chord where that goes through the center of the circle. If you have a line that only intersects the circle at one point. So if we're only intersect at one point, it's called a tangent to the circle. As a matter of fact, actually, if you take this line here, this is actually, one can show that this is actually perpendicular to the tangent. Let's draw a new circle. Here we can have the center point, let's call it C. And then we have two radius. Here we have A, B. Then this part here of the circle, that's called an arc. It's the arc of the circle. The angle we have here is called the central angle. And this part of the circle is called a sector. If we instead take a point, instead of the center point, we take any point here on the circle, then draw these here, these lines segments. These are called, or this angle here is called an inscribed angle. So this is an inscribed angle, and here instead we had a central angle. So they go to the two same points here, but one goes from the circle, the other one goes from the center. If you have a circle and the radius r, then the area of the circle is pi r squared, and the circumference is 2 pi r, or if you like, pi times the diameter. So this holds for a circle. So how can we come to these two formulas? Yeah, we can, for example, use this. Let's draw a regular polygon inside the circle like this. So all these are equal, have the same distance, so you have the same size. All the triangles here are identical. Now it's possible by geometry to show that if you add the distances here of all these red lines, and then we will start to increase the number of regular polygons, or number of edges we have in this regular polygon. So here we start with 1, 2, 3, 4, 8, and then we can increase to 20 and 100 and so on. If we increase more and more, this will become closer and closer to this formula here. So we can show that in that way. And for the area, we can instead do in the following way. So if we instead divide up the circle in this way, then we see that we can, by moving these slices here, we can form this figure. And by increasing the number of slices, this will become closer and closer to a parallelogram. And we know that the parallelogram, we just take the base length times the base height. And then multiplying these two, we will get this formula. So that's how we can motivate these two formulas. The next thing we want to talk about are similar figures and congruent figures. These two figures are similar. They're called similar. And the reason for that is that they have the same shape, but not necessarily the same size. These two have both the same size and the same shape. So they're called congruent. We see the mirror image here of each other, but that doesn't matter for the congruency. So similar means same shape, congruent means same shape and same size. Okay, so that's what we want to study a little bit closer here now. So if you call this figure A, this B, you can write this symbolically as A similar to B. and if you call this C, D, you write this as C congruent. You write like this to D. So if you take a figure like this, or any figure, then you rotate it, move it around, or maybe take a mirror image, then you will get a congruent figure. Or if you have a figure, then you enlarge it or make it smaller, then you can make a similar figure. For example, if you have a map, then the map is is similar to the reality. So if you have a map that is similar to the reality, it has the same shape, but not, of course, necessarily the same size. And if you have an enlargement of something, for example, bacteria, then you also have a figure. This figure is similar to reality. In this case, when you have similar figures, you can talk about the scale. For example, the scale is written here in the figure. That means that for example, 1 centimeter in this picture corresponds to 2,500 centimeters in reality, or that 1 centimeter here corresponds to 100,000 centimeters in reality. So here we talk about scale. Scale is a ratio between length of one object and the other. So for example, if you have two circles, and two circles are of course similar. So let's say that the radius of one is 2 meters and the other one is 5 meters. Then you have the scale between these is 2 divided by 5, 0.4. So the scales between the figures is the ratio between two corresponding lengths in the two figures. If you have two polygons, and the two polygons, these two polygons are similar if all corresponding angles are the same. So this angle corresponds to that one, if this is same as that, and that holds for all the angles, and that all the edges, the distances of the edges, all are proportional with the same proportional constant. So for example, this is 2, this is 4, and this is 1.5, and this is 3. If all distances are proportional, here with the factor of 2, then we have two similar polygons. And if they have all the angles same, if the polygons have the same angles, but also the same distances, so the corresponding distances are the same. So if this distance is the same as this one, then the two figures are congruent. So for example, if I take this figure and rotate it at some angle, then we get a new congruent figure, because all the corresponding angles will be the same, and also the length of the edges will be the same. Since polygons can be quite complicated, let's look at the most simple polygon we can have, and that is a triangle, of course. So we have some triangle. How can you decide if two triangles are similar or not? And how can you determine if two triangles are congruent or not? Then let's say these two, for example. How can I decide if these two are similar or congruent or neither? Yeah, of course they are similar if that angle is equal to that one, and this angle is equal to that one, and this angle is equal to that one. And if all the corresponding sides are proportional, so for example that is 2, that is 4, and this is 3, and that's 6, and that's 5, and that's 10, then they're all proportional. In this case they are similar. But are there some other way we could check without just checking in the figure like this? Is there some other way we can check if two triangles are similar and congruent? Yes, there is. We have some conditions, and if they hold, then we know that the triangles are congruent and similar. So let us start with congruent. If any of I will write now 3 conditions. If any of these 3 is satisfied for the situation we have, then we know that the two triangles are congruent. The first condition, let's call it SSS. And then if we have this edges of the edges or sides, you can also call sides, edges of the triangles, if they are pairwise, have the same length. So edges pairwise, same length. Then we know that they are congruent. So this is a theorem one can show that if you have edges pairwise same length, so for example this one is same as that, that is same as that, then we know that they're congruent. Then we don't have to check that the angles are the same, because if all the edges are the same, then according to this, then we know all the angles are also the same and they are congruent. The next condition, let's call that SVS. And if we have instead of 3 sides same length, and if you have only 2, so two edges and they're in the angle between them is the same. So for example, if that's equal to that, and that's equal to that, and that these angles are also the same. So if you have that, then we know that the two triangles are congruent. So we don't have to check that every angle on every side is the same, or an edge is the same. We only have to check that 2 of them and the angle between them is the same. Then it follows from this that it will be congruent. And the third condition that will say that they are congruent is if 2 angles and the edge between the angles is same. So for example, if you know that this angle is the same as that one, this is the same as that one, and we know that these sides have the same length as that one, then this condition says that, okay, these two triangles are congruent. So if any of these 3 holds, then we know that the two triangles are congruent. Then there is also a fourth condition, but we will not use it here in this course, so we'll skip that. But there is also a fourth one can use, but it's a little bit more complicated. We will skip motivating these 3. We will just accept that these 3 will give us the right conditions for congruency. Let us take an example to see if we can determine if 2 triangles are congruent. For example, let's say that this side here is 23, 35, 29, and 35, 29, 23. Then according to condition number 1 is satisfied, because this is equal to that, that equal to that, and that equal to that. 3 sides or 3 edges have the same length. Then we know that they're congruent. Okay, let's take another example. Let's instead say that we have the following situation. So we have 40 degrees here, 40 degrees here, and then we have 19, 34, and then we have 34 and 19. These are also congruent, and that's due to the satisfying the second condition. That is, 2 edges have the same length, and the angle between them is the same. Then we know that they are congruent. And as a third example, let's say that we have like this. Okay, I won't bother about this figure being really congruent, I'm just taking some examples. But let's assume that now that we have an angle here, let's say that this is 38 degrees and this is 97. Of course, that's not true from the figure, but we just after now the numbers here. And let's say that this is 97 and this is 38. And let's say that this is 20 and this is 20. So let's say that this is a situation we have. Then we can say from the third condition that is satisfied. And therefore we can conclude that these are congruent. And that's because two angles are the same and the edge between them, connecting them, is the same. So therefore we can conclude that they are congruent. In a similar fashion, we have three conditions that can determine if two triangles are similar. So if one of these three conditions is satisfied, then we know that the two triangles are similar. And the first condition we write as SSS with a wiggly line. And this condition is that the edges are pairwise of equal length. Not equal length, or proportional, or pairwise proportional. Okay, so if the edges are pairwise proportional, then the two figures are congruent, or the two triangles are similar, I mean. So let's take here now, let's say that this is A. Let's call it A prime. Yes, these are two different. And let's call this B, and this B prime. This C and this C prime. If we have that A prime divided by A is equal to B prime divided by B, this is the length of the edges. And if you have C prime divided by C, if these all are equal to the same number, then the edges are pairwise proportional. Then we know that they are similar. Means that all the angles are pairwise the same. So the angle between A and B, this one, is the same as that one. The angle between B and C are the same, and so on. All angles are pairwise the same. Not all of them equal to 60, but they're pairwise equal. So that angle is equal to this angle. So that's the first condition. So if this holds. The second condition, so any of these conditions can hold. It's enough if one of them holds. The second one is that two edges are pairwise proportional. So pairwise proportional, and the angle between them is the same. Okay, so let us take an example here now. Let's say, let's get rid of C for a moment. So let's say that we have this situation. So we know that the angles between A and B here and A prime and B prime, they are identical, they're the same. And we have these conditions, that we know that that one is proportional to that one with the same proportional factor. This is the case. Then we know that these two triangles are similar. And the third condition, let's call it VV. If two angles are the same, if that holds, then we know that the two triangles are similar. So this does not include the sides at all, or edges at all, the length of them. So let's take these two angles here. So let's say that this one is equal to that one, and that is equal to that one. Then we know that these two are similar, according to because they are satisfying the third condition. So if any of these, just enough of one of them to be satisfied, then we know that these two triangles are similar. Okay, so let's say we have this situation. So we have these two triangles. Then we will see that this will satisfy the second condition. That is, two sides are pairwise proportional and the angle between them is the same. So we see here the angle is the same, so that we can see directly. Now we want to check if these are pairwise proportional. So see that this here corresponds to that one. So if you have 16 divided by 12, what's that? That's 4/3. And if you take this one, divide by 15, if that's also equal to 5/3, then they are pairwise proportional. And it is because this is 4 times 5. And this is 3 times 5. This is also equal to 4/3. So they are pairwise proportional and the angle between them is the same. So that means that these two are similar. And we will skip the other two conditions. They are similar to how we did this and earlier examples. The final thing we will go through in geometry is solid geometry. So far we have studied geometry in 2 dimensions. Now we will look at geometry in 3 dimensions. Okay. So then we first have to have some definitions. So in solid geometry we talk about solid figures. So if you have here a 3-dimensional figure, that's a solid figure. Or for example, a cube. This is also a solid figure. So now we want to study these kinds of figures. What is a polyhedron? So a polyhedron is a 3-dimensional solid figure that is contained by plane polygons. That is plane surfaces. So for example, if we have something like this, now we have to look at it 3-dimensionally. So let's say that we have a solid figure looking something like this. Here we have polygons, plane polygons, making up the faces, you call the faces of this polyhedron. Each plane polygon here is called the face of the polyhedron. Okay, so if you have that, then we're talking about the polyhedron. And here we have the corners or the vertices, if you can also call them. Okay, so an example is, the thing we have drawn here is an example of a tetrahedron. So we can, if you have, just sketch it again. We have something like this. Let's call it tetrahedron. So that's an example of a polyhedron. Or you could have a cube. That's also a box-shaped object like this. But let's say cube. That's also a example of polyhedron. But now it doesn't have to be cube. If you have 6 faces, so if you have 6 faces, this is called a hexahedron. So the size here doesn't have to be squares and not same size. But the point here is there are 6 faces to it. Then we call it a hexahedron. Here are 4 faces. Then we call it a tetrahedron. Okay, so we have faces, corners, or vertices, and edges. if we have a, for example, if we have a figure that is made limited by or made up by regular polygons that are congruent. So we have regular polygons. They're all congruent. For example, a cube. So if you have, for example, a cube, then that's called a regular polyhedron. So a cube is an example of that, but it's not limited to that. But all the faces here are regular polygons. So a normal die, for example, is an example of that. So, for example, here we have a polyhedron. And here we have a tetrahedron. And a hexahedron. And this is a cube, which is an example of a regular polyhedra. Then in this figure here we have something called a prism. So what defines a prism? Well, a prism is a polyhedron, but where two of the faces here are congruent. So these are congruent polygons here, these two. Or it could be any two, but two of them are congruent. Then it's called a prism. So this is a special case of a polyhedra, or polyhedron, I should say. And this side here, and this are called the base. So this is called the base here. And if the base is 90 degrees to the height here, in the height in the prism, this is called a right prism. So you see here is not necessarily 90 degrees, it's tilting the whole thing. But if it's 90 degrees, so that the parallel lines here are 90 degrees to the base here, then we have a right prism. And this example here, it shows a rectangular cuboid. That's the limit of the rectangular cuboid. So what is that? It is the same as a right prism, but where the bases are rectangles. So this here is a special case of this one, where the bases here are rectangles. And if instead of having right prism where the bases are rectangles, but if they're instead parallelograms, this is called a parallelepipede. So this is a special case of a right prism where these bases are parallelograms. A cylinder. If you have a plane, so let's say that this side is h long, and this has the length, some length here now. If we roll this up, so we roll up this longer side of a longer edge of the rectangle, so that becomes the circumference here. So we make this figure. So the height of this solid figure becomes this length here becomes the height of this solid figure, and this is circumference. It corresponds to this one. So here we have a radius. So this length is the circumference of this circle here. So this is 2 pi r. So the circumference on that one. So if you have a plane and roll it up like this, then we will have made a cylinder. So this is an example of a cylinder. So this is 2 circles here connected by this rolled up plane. This is called the height of it. The height of a prism and the height of the cylinder, they're similar here. They're from the bases up to between the bases, like this. For both a prism and a cylinder, they are similar, but instead of having a polygon, this is just a smooth one, infinitely many edges. We call it circle instead. But since they're so similar, they have the same formula for calculating their volumes. So the volume of a prism is given by the same formula as the volume of a cylinder. So we have that the area here of this circle, we call A, multiplied by the height, that will give us the volume of the cylinder. And we could, for example, go back here now to this. So if you have our prism, you have a prism, so we take this area here, we call it A, multiplied by height, we also get the volume of the prism. So we see it's the prism and the cylinder are similar figures. Okay, so both are given by this formula. Okay, so let's say we have some polygon, some arbitrary polygon, and we take a point outside that, and we connect that point to every vertex of the polygon, like this. Then we have made what is called a pyramid. This is a pyramid. And we have the height of the pyramid. We have this distance here, so we take 90 degrees up here. And let's say that this base area here is A. Then the volume of this one is given by H times A times H divided by 3. So it's similar to the same formula as the prism and the cylinder, but we have to divide by 3 since it narrows up. Okay, so this is a pyramid. Similar to a pyramid, we have a cone. So instead of a polygon, we have a circle and have a point outside the plane of the circle. And then we connect this to this point. So similar to a pyramid. Then we will have a cone. So here we have the height of the cone. Radius. Okay, how can you form this figure? You could make it by taking a circle, a part of a circle. So if you take a sector of a circle, and here with radius r, and then you roll it up. So you roll it up, so this part, the arc here, becomes this circle here. Okay, so then what's wrong here? We shouldn't write radius here. So that the radius should now be this one. So this edge here becomes a radius here, and the circle here corresponds to this arc here. Okay, and then the height will become in this solid figure like this. So that's how we can form a cone. But the cone is similar to a pyramid. So the volume of a cone is also given by the same formula. So the bottom base area times the height divided by 3. So that's the same formula for that. And then finally we have a ball or a sphere. Okay, so if you draw a sphere here, something like that. Then we have a radius, or we could just as well draw it wherever. From the center of the ball, we have a radius of our ball here. Okay, so if you take all the points that have the same distance from the center, then we will form a ball or a sphere. So if you take all the points inside the sphere, then we call it the ball. If you only limit to the surface, it's a sphere. Okay, what is the area of this ball? And what is the volume? Perhaps the volume is more familiar. If you take a volume of this ball, it will become 4 pi thirds times radius to cube. And the area, surface area of the ball, or the area of the sphere, is 4 pi r squared. So this can also be shown to be the case. So that was the final example. So this, you see, there are a lot of definitions involved in geometry before you can get started. So what really remains now is to do a lot of exercises. This is only half of the part going through the theory, so you have to calculate a lot of exercises. And then again, recommend reading the books in the description, the links there to my books, because there are a lot of exercises you can do. Okay, so that concludes the geometry.